Welcome to module 1, lecture 5 of concrete technology. Shall be discussing on types of cement and its use today. We just started that in the last class in fact. So, continuing from that point, we will be proceeding today. We just mentioned in the last class that by manipulating the chemical composition of the compounds of cement, or in other words oxides composition of the cement, which in turn allows you to manipulate the compound composition of cement somewhat, and then by changing their physical characteristics we can alter the properties of the cement and their performance in concrete. Thereby, we can get different varieties of cement. In addition to this, other material, other supplementary cementitious material like various pozzolana, I will mention what they are, or some other material such as limestone powder. So, by using those materials you can get additional cements which are known as blended cements or composite cements. So, we will look into those as well. So, pure cements, blended and composite cements, this is what we will look into. So, general outline of our discussion would therefore would remain type of cement, followed by lime, followed by supplementary cementitious material such as fly ash, slag, silica fume, etc. So, therefore, we can look into first the pure cements and the modified cements. What we said, I repeat it again, by modifying the composition and physical properties, performance of cement can be changed favorably to obtain different types of cement. So, composition, chemical composition of the cement can be changed, and their physical characteristics can also be changed in order to get different types of cements. So, what are the types of cements? Well, ordinary Portland cement is the most commonly used cement for many years. However, currently perhaps it is not the most commonly used cement, because some of the blended cements have become quite popular all over the world. This cement is known as type 1 cement as far as American Society of Testing Material ASTM, or cement 1 SEM 1 as per EN 197-1, that is the European standard. So, is the case with Indian or any other country standard. In Indian standard, IS 269 deals with 33 grade of OPC cement, and other cements like 43 and 53 grade, which are classification by Indian standard, they are OPC, also OPC grade. So, OPC is 269, they are called OPC cement simply. Now, this is specific to Indian scenario. We talk of OPC grades 33, 43 and 53. Grade 33 is that cement which exhibits 28 days mortar. Yesterday or last class we discussed about strength test of cement. So, 50 centimeter square base mortar cube test. When you do, if the strength is more than 33 MPa, F, that is strength, if it is greater than 33 MPa, then you call it grade 33 cement in Indian context. Similarly, when it is more than 43, the strength is more than 43 MPa, 28 days standard mortar cube strength is more than 43 MPa, you call it grade 43. and if it is more than 53 MPa, then you call it 53 grade. And we have 3 different codes for this. This is IS 269 deals with this one, this particular one, and that is the originally used ordinary Portland cement. So, that is as far Indian standard is concerned. ASTM of course classify OPC as type 1 and OPC as type 1, SEM 1 is what EN 197.1 says, that is the European standard, right. BS standard also used to call it, I mean now it is all integrated, all European codes are integrated, and this is SEM 1 as per European standard. Then the next cement is rapid hardening Portland cement, RHPC stands for rapid hardening Portland cement. So, rapid hardening Portland cement, it is ASTM type 3. So, RHPC there is a code, in Indian code of course there is RHPC. So, this cement hardens fast. So, you get the strength, possibly 3 days strength in 1 day, 7 days strength in 3 days, and 28 days strength is nearly 3 days, 7 days, and so on and so forth. So, you get high early strength, you get high early strength, high early strength. We will look into it how it is obtained. So, high early strength, high early strength, that is the characteristics. Special RHPC, which could be with OPC plus calcium fluoroaluminate plus a retarder. We will come back to this a little bit later on. First, we will try to understand what is RHPC, OPC. Maybe we will come back to this slide again back if required. So, that is special rapid hardening cement is one which hardens much faster. So, they are basically fluoroaluminate type of cement. Then you have got low heat Portland cement, ASTM type 4. Now, this is ASTM type 3 and this is ASTM type 4. Now, ASTM type 4 is low heat cement, Now, low heat cement was used largely, largely for mass concrete construction earlier, right. It was used earlier for mass concrete construction. So, this type 4 heat of hydration produced is low. So, that is why it is called low heat cement. Rate of heat evolution will be low, and how it is done we will look into. Then sulphate resisting cement, which is ASTM type 5. I will come to type 2, ASTM type 5 is sulphate resisting cement, and again we will see how these cements are actually, how do we manipulate the composition of the compounds in cement to obtain all this. Then of course, we have blended and composite cements. Supersulfated cement is a sulphate resistant cement. We will come back to this slide a little bit later on, and white cement is used for decorative purposes. Expansive cement used for filling in grout holes or shrinkage compensating cement. So, you want to fill in cracks or similar situation. Oil well cement is used in oil wells, petroleum, crude oil wells. Actually, they have special setting characteristics, specific setting characteristics, stringent setting characteristics, and of course, they should be sulphate resistant. So, we will look into some of this in details, and maybe we will come back again to this slide if required. Now, if you recall, SEM 1, that is your type 1 cement, ASTM type 1 or OPC, this is OPC, had roughly around 59% of C3S, 15% of could be something of this order, 15, 20, 55, etc., etc. This is one OPC, let us say C3A12, C4F8, and calcium sulphate, this is 2.9, and free lime could be something like this, loss on ignition 1.2. So, this composition will satisfy OPC. This composition will satisfy OPC. Now, if we recall that high C3S means relatively high early strength, high. So, this is slightly higher, could be even less, something like 54, 54, 55, etc. So, high C3S means high early strength, C2S means later strength, C3A means heat of hydration, high heat of hydration, it contributes maximum to the heat of hydration, and this has of course much less effect. Calcium sulphate again does not have much of an effect anywhere, and free lime of course is as restricted as anywhere it should be. Loss on ignition should be almost similar for all. So, major effect comes from the quantity of C3S present, and C3A present has got a role in type 4 cement, which is low heat cement. So, let us see one by one. Type 2 cement is called modified cement. It is actually somewhere between type 4 and type 2. It is not exactly low heat, but it is between these two. So, let us go downwards. Type 2, I will come to type 2 later on, come to type 3. Now, this has got the highest C3S. This has got the highest C3S, therefore, it has got the highest C3S, therefore, it would give you high early strength. Remember, recall type 3 is nothing but RHPC, rapid hardening Portland cement, and it has got the highest C3S, least C2S compared to this two, it has got the least C2S. So, it will have high early strength, least long term strength would not be there as much, and C3A content is relatively high again, not very high, almost similar as OPC. C4 content, AF content is almost similar, rest of the things are more or less similar. Now, therefore, this cement is rapid hardening cement, because chemical composition wise this has got the highest C3S. Physically of course, fineness governs high fineness. Higher the fineness, rate of hydration will be high, and therefore, strength development will be faster. So, physically RHPC has two things, C3S is highest, C2S is least, because after all if you increase the C3S you have to reduce down something. So, CTS, C2S, so it is highly alite, lot of alite component, belite is less, and then it has got high fineness, that is why it reacts faster than any other cement, So, therefore, rate of hydration is more. So, that is rapid hardening Portland cement. A very special variety of this will have high fineness, which you want to set even quickly, a jet cement, which will set very fast. Now, some special cement of this kind can be developed using composition of fluoroaluminate. You see, special rapid hardening Portland cement can be generated with calcium fluoroaluminate and some sort of retarder. So, this reacts extremely fast and sets also very quickly, and it is grinded to a very fine level. So, this cement is likely to be costly because you are grinding it. So, grinding energy, you spend some energy in grinding, and therefore, it is likely to be costly. So, that is what is a rapid hardening Portland cement is, and special rapid hardening Portland cement uses calcium fluoroaluminate with OPC and retarder, and that gives you fluoroaluminate system can give you high RD strength. So, now next we can go to type 4, which is low heat cement. Now, what gives heat of hydration maximum? The maximum heat of hydration comes from C3A. Maximum heat of hydration comes from C3A. So, therefore, you can see the reduction here, maximum heat of hydration is here, therefore, this is reduced. C3A content is only 5%, and further to reduce the heat of hydration, because this reacts early, C3S reacts early. So, this is also much less, but long term strength will be better. So, you put higher C2S. So, this is low heat cement, low heat cement. Rest of the things, of course, there is some changes, but not very significant, marginal. So, a low heat cement will have less C3A, less C3S, less C3A as well as less C3S. Then something has to increase, and it is the C2S which increases. It will not have extraordinary grinding. In fact, the Blaine's fineness in case of type 3 would be much higher than type 2, but here the Blaine's fineness may not be higher. It could be same as 225 meter square per kg minimum, and this could be much higher, maybe 350, 400 or so, or even higher depending upon the type, how rapid hardening you want, maybe 700 meter square per kg and so on. So, depending upon that situation. So, this is type 4, this is type 4, this is type 1. Now, 2 is in between, which is called modified cement as per American Society of Testing Material classification. So, this is type 2 cement. STM type 2 cement is modified cement, type 2 is the modified cement, as we call it, it is the modified cement, and modified cement is something in between. It has got low heat of hydration, but not as low as this. Low heat of hydration also means the strength development rate will be slower, therefore, your demolding time will be higher. So, this is compromise between the two. Low heat is modified cement is compromise between the two. It has got somewhat higher C3S than this, and obviously, C2S also will be lower than this, but higher than this. C3A content is also more than this, etc., etc. Now, why do you use OPC? Well, most of the construction was carried out with OPC earlier, but in a mass concrete you can't use OPC, because heat of hydration is very high. In mass concrete, large size has got volume to surface area ratio very high. Surface area is small, volume is very high. If your thickness of the lift, a particular lift, your concreting lift, because concrete casting is done in stages height wise. So, if you have a very wide, very large area and with sufficiently large thickness, which is the case in case of say gravity dam, some of those plain concrete retaining wall, etc., etc., strength is low, but the heat of hydration is usually required strength of the concrete is usually low, but heat of hydration is a point there, because of the surface area being small compared to the volume, or surface area per unit volume being small, heat dissipation rate is generally small. Now, if the surface is not able to dissipate the heat, there will be surface is not dissipate the heat sufficiently from the core. So, it can so happen that core is at higher temperature compared to the surface. Surface is in contact with the outside air. So, it has lost the heat, but the heat coming from the core to the surface, that will depend upon the thermal properties of the concrete material, concrete system, and it is not very high, it is a nearly insulating material. We will discuss about that sometime later on, but heat from the core of the concrete is quite often is unable to reach to the surface. As a result, differential temperature gradient may exist in case of mass concrete, very thick raft and such situations. But you do not and this differential temperature, if it is existing, can cause cracking, because inside is warm, outside is cool. So, differential contraction can occur, and that can result in cracking. So, we will look into that cracking later on, but what we understand at this moment is that heat dissipation is a requirement for mass concrete. Now, well, if I generate, you can stop heat generation itself, so that dissipation required will be less. So, therefore, you use low heat of hydration cement. So, low heat cements are used in mass concrete, and that is why you reduce down your C3S content. So, usage of low heat cement is in mass concreting. If you look at rapid hardening cement, you like to use it in places where you want the strength gain to be very high. For example, where you want to pre-stress the structural element, you want to apply pre-stressing force, you apply external force early, load has to come early, let us say, or pre-stressing force has to come early. Perhaps you are aware of what is pre-stressing. You pre-stress the concrete in compression, so that it can take lot more tension than it was capable of withstanding without pre-stressing. So, that again we might discuss that sometime later on, in some other context. So, where you want to do early, you want to release the mold early, you want to pre-stress the concrete, etc. Wherever you want high early strength, there you will be using rapid hardening Portland cement, but it is costly. The second aspect is quick setting, that is a separate issue. Setting is quite, setting required. Rapid hardening Portland cement do not have setting time, early setting time. It sets same minimum 30 minutes, same specification as the ordinary Portland cement. But you can have something called quick setting cement, might use it in repair work, maybe some sort of construction in underwater or near stream and things like that, where you want it to set early. A jet cement will of course set very fast. So, the usage of these two cements you have seen, 3 this cement 3 and this 2. 2 is somewhere in between. So, therefore, where you do not want that kind of heat of hydration as this generation, low heat of hydration as this, but you want some strength development, there you will be using this, because this will have very slow strength development. You have less quantity of this and you do not grind it too much. So, you will have lower strength development. We will look into the strength development sometime later on. This one has got a very high early strength, but later strength is not good. Even that can have problems related to durability, etc., etc. But at the moment, this was the purpose why rapid hardening cement, usage is where you want early strength. Now, coming to type 5 cement, this is sulphate resisting cement. Now, we shall see that when we talk of durability of concrete, that sulphate attacks concrete through C3A. Well, we can remember, or we can recall our discussions, earlier discussion, we can recall our earlier discussion on ettringite formation. We discussed the formation of ettringite. If you recall, we added gypsum to cement while grinding in order to control the setting property, and gypsum reacts with C3A. Now, gypsum occupies more volume than the original C3A and gypsum combined. So, gypsum combines with C3A forming ettringite, that is what we have seen earlier. Now, this occurs in plastic concrete, no problem. Ettringite occupies more volume, well, no problem, because this can be accommodated in a plastic concrete without cracking. But if gypsum or for example, sodium sulphate comes in contact with the concrete, moist concrete, or in presence of moisture, sodium sulphate can react with calcium hydroxide to form calcium sulphate, and this calcium sulphate can react with C3A hydrates forming ettringite, and this ettringite now if it tries to occupy more volume than the original reactants, it will cause cracking of the concrete. That is sulphate attack. Anyway, we will discuss this at length sometime later on, but at the moment what we got to understand is it is C3A which is responsible for sulphate attack. Sulphate attack takes place through C3A. So, therefore, in this cement you have least C3A 4 to 5 only, very small quantity of C3A. So, a sulphate resisting cement will have least quantity of C3A, but then C3S is also reduced and C2S is also reduced. C2S is also reduced, increased somewhat than this. So, C3A is C3S is reduced, but main aspect is that it should have low C3A in case of sulphate resisting cement. So, these cements we have looked into right now. We will go back to the first slide again. So, physically rapid hardening Portland cement high fineness 325 meter square per kg minimum blends enables early removal of formwork setting same as type 1. As I mentioned, special rapid hardening Portland cement OPC plus calcium fluoro aluminate retarder, sometimes this retarder is the citric acid, setting time can be controlled. It has got a very high specific surface 700 to 900 meter square per kg blends specific surface, which we discussed yesterday. Low heat Portland cement ASTM type 4 heat of hydration is 250 joules per gram at 7 days, adequate fineness to control strength gain. So, adequate fineness to control strength gain. Modified cement ASTM type 2 higher rate of hydration than type 4, it is in between, and type 5 of course is sulphate resisting cement low C3A, that is the characteristics. I will come to blended cement. Let us go back to some of the cements those who are there in our first slide. So, let us go to the first slide again back, right. So, we have looked into this cement, we have looked into this cement, we have looked into this cement, this cement. So, we will be looking now into blended cements, super sulphated cement. Let me just tell you right away and talk about white cement and expansive cement now. We will come back to the other cements later on. Super sulphated cement is prepared from ground granulated blast furnace slag. We shall see that ground granulated blast furnace slag, ground means grinded, granulated blast furnace slag. We will come to this again. GGBFS actually GGBFS has got almost, it has got same oxides as the cement. We will see that a little bit later, and high quantity of this material is used in super sulphated cement, around 80 to 85%, mainly meant for sulphate resistance, and 10 to 15% of gypsum with 5% OPC. So, you can see that it is not really with OPC, but with granulated blast furnace slag, ground granulated blast furnace slag is the one which is through which this cement is prepared. So, this is super sulphated cement. Now, properties of ground granulated blast furnace slag we can see. This will not have C3A at all, no C3A, no C3A in this one, no C3A in this one. So, the reaction of sulphate is expected to be simply not there. So, it is supposed to be highly sulphate resistance. White cement essentially is prepared for aesthetic purpose and prepared from China clay, which is white, and calcium carbonate source used is chalk. Now, both are white because they are more or less pure, right. Now, no iron should be present there, no other oxides which can add color to it. So, therefore, this cement is costly, very costly, because you are producing from certain specific raw material, China clay and chalk. So, it same all similar properties, same like OPCs, similar type of composition would be like OPCs, but only thing is no iron, no other such oxides which can add color. So, this is why it's white cement, and it is used for where you want aesthetic. One example, of course, in India, in the city of New Delhi, is the Baha'i temple, the lotus temple. It used white cement because it is absolutely sparking white, and then marble stones, white marble stones have been used as aggregate. So, it is totally white, completely white. So, when you want to give a complete white look, this is what is used. Expansive cements or shrinkage compensating cements are those ones which are used to fill in, let us say, crack or gap or grout holes, so that after expansion it will compensate the shrinkage, right. So, the system essentially involves tricalcium, sometime lime system, sometime aluminate system. Aluminates, same attringite reaction is utilized. Maybe I will discuss this a little bit more later on. Oil well cement has got high sulphate resistance and setting properties are strictly controlled. Anyway, now we can go further ahead and discuss on the other issues of uh, different types of cements. Blended cements, for example, blended cements. Now, this blended cements uses pozzolana, a material I might have mentioned earlier in the history when I was talking in the introduction, right. So, that is what, yeah. So, before that, just expansive cement, let us cover it up fully. High alumina cement with OPC and gypsum, because you see attringite formation would occur with this one, high alumina cement and gypsum, and this attringite occupies more volume than the original reactant, therefore, it causes expansion. So, expansive effect of high alumina cement together with OPC and gypsum is used in expansive cement. Other compositions are gypsum, bauxite is aluminum ore and chalk. So, they are burnt together. So, they are produced similar sort of things are produced, but burning gypsum, bauxite and chalk together, and this forms expanding agent that can be used in OPC and slag. So, this is what is a expansive cement. There are some lime based expansive cement as well. The strength that we are looking into, if you look in the, because different types, type 1, type 2, type 3 and type 4, type 5 cements, if you look at it, right. Now, type 1, if you see, this is our OPC, strength development is somewhere here. Type 3, high early strength. So, it has got high early strength, but its long term strength is in fact slightly lower than the OPC. Modified cement, if you look at it, this is modified cement, type 2 somewhere there, modified cement. It has got low initial strength than OPC, but long term strength is better, because more C2S. Type 4 has got least initial strength, right, which is low heat, because it has got less C3S as well. So, more C2S, as we have seen earlier. Since it has got high C2S, it has got better long term strength, but very little early strength. Heat of hydration is low, that is the thing, early strength requirement is not there. So, we will not use this cement where demolding, early demolding is a requirement, surely not use this cement. Sulphate resisting cement has got properties less C3A, less C3S. So, somewhat lower early strength than type 1 or OPC cement, but long term strength is again better than OPC cement, surely. So, this is how the strength development of different cement takes place, and now we understand also why does it occur that way, because we know what are the compounds there and what is the physical properties. Finest physical properties will be of rapid hardening Portland cement, and it will have maximum C3S. Low heat cement will have least C3A and C3S. Sulphate resisting cement will have low C3A, and naturally C3S is also reduced a little bit, and therefore, the strength, initial strength is low. So, all these cements has got initial strength low, but they have got better long term strength. This cement has got better early strength, but long term strength is worse than the ordinary Portland cement. Now, let us come to blended cement, but before that let us understand a little bit about this material lime. As I mentioned in the very first day's discussion, module 1, lecture 1, we said that lime was used as a cementing material prior to cement. Currently, of course, used for repair of historical monument to match the properties of original material. So, lime has been in use as a construction material much before actually cement was invented. Lime has been used as I said, that is reported, it has been used something like 7,000 years back, as reported by Professor Aaron Bentur in one of his article in 2000 around 2001. So, this has been used for 7,000 years. Now, in India of course, we have used lime together with what is called surki, which is nothing but when you burn the clay, the dust that remains below the brick kiln is called surki. So, it is burnt clay, some form of fine powdered burnt clay, we will come to that. Now, lime itself are two types, hydraulic and non-hydraulic lime. Non-hydraulic lime sets when excess water evaporates and calcium hydroxide reacts with carbon dioxide to form calcium carbonate. So, non-hydraulic lime sets when it has got excess water and that evaporates, and carbon dioxide from the atmosphere will react with it forming calcium carbonate, therefore, the setting occurs. Hydraulic lime on the other hand, it has got active clay and reaction of lime with clay leads to cementing property. So, hydraulic lime and non-hydraulic lime, this will have some active clay in it, and reaction of clay with lime causes leads to cementing property. Now, this is what has been used for many years. So, what we know is that some materials, some silica can react with lime to produce CHS gel like structure. Lime with clay, that is what we said, lime with contains active clay and reaction of clay and lime leads to cementing property. Now, this was actually discovered pretty early, like volcanic ashes I mentioned in Roman civilization. They used volcanic ash together with lime and they found that it can give the similar cementing property. In India, as I said, lime and surki. Now, surki is after burning the clay, the dust that is there, fine particles which are there, that is what is surki. So, if that is nothing but bricks are manufactured from clay. So, therefore, that is nothing but burnt quickly, you burn the clay, heat it up, I mean not burning, really heating it up to sufficiently high temperature, maybe 1400 degrees centigrade, and cooling it rapidly because that dust which comes out from the clay bricks, they just get deposited onto the ground, and therefore, they started losing their heat very fast, rapidly starts cooling, and the finer ones of those one can react with lime, and that is what has been used in many of the monuments. Lime surki construction has been pretty well known. Similarly, the volcanic ash with lime also can react and produce cementing material. Now, these materials are nothing but, you see, lime is calcium. If it was lime means calcium hydroxide plus the silica or alumina in presence of water. So, you see the same ingredients as the cement. So, actually they produce CHS and gel, CHS gel. Now, from the original name of the volcanic ashes, this class of materials are called pozzolana, right. So, the pozzolanas are those material, they are basically reactive silica which reacts with lime in presence of water to produce CHS gel. Volcanic ash are natural pozzolana. Surki of course is not natural pozzolana. So, there are many natural pozzolanas, but there are certain other industrial, I will not call it waste nor call it byproduct, but I will call it industrial product, because from for a student on concrete technology it is not a waste product, but thermal power plant would of course they treat this material as a waste. So, many other products from industrial products, they also show this kind of property, pozzolonicity or pozzolanic behavior, that means they react with lime. Now, consider this material fly ash, it is a product from thermal power plant collected at electrostatic precipitators, right. thermal power plant collected at electrostatic precipitators. I will discuss this somewhat in more details when we talk of mineral admixtures. Coal as obtained from the mines contains lot of impurity, mainly the clay, because clay is the material abundantly available on the earth surface, earth crust, top of the earth crust, or from those zones where we mine the coal or do any mining for that matter. So, whenever you are trying to extract anything from the mines, it contains sufficient amount of clay. This clay, which is present as impurity in the coal, is grinded together with the coal. If you wash the coal, of course, some of it will go away. However, it is impossible to remove all this clay from the coal, from the ore actually, and this coal is, I mean sorry, from the coal, and the coal is grinded, and after grinding the coal is burnt. The coal is carbon, the carbon, sulfur, they will actually get converted into carbon dioxide or sulfur dioxide, etc., and many other NOx and so on, many small quantities of those are also there, they will go away. What about clay? It is SiO2, Al2O3, SiO2, Al2O3, etc., Al2O3, Fe2O3. These materials will remain. Now, since they are very those fine ones from this, they will remain as ash, they will remain as ash. Now, this ash material, the finer ones from this ash material will actually go away with the flue gas, and it is trapped in electrostatic precipitators. We will discuss this at somewhat more at length when we talk of mineral admixtures, slightly more. So, they will be captured at electrostatic precipitators. For environmental reasons, you can't throw them to the environment, because they are health hazard. So, it is collected in electrostatic precipitators, and if you can handle them dry, then this material shows pozzolanic property. In other words, this is actually clay grinded, heated to a very high temperature of around 1800 degree centigrade, and then suddenly exposed to air at 25 degree centigrade. So, they rapidly cool, like surki which cools rapidly, like volcanic ash which cools rapidly. The clay material heated up very fast and then cooled rapidly. This material is also cooled rapidly. So, when you cool rapidly, actually its structure remains amorphous. So, fine amorphous material, and amorphous material can react compared to crystalline materials which are stable. We will discuss this point sometime more, sometime during mineral discussion on mineral admixtures, more onto this. So, fly ash is a pozzolanic material, but not only fly ash, ground granulated blast furnace slag, actually iron ore also contains clay as impurity, and when one wants to remove it in the blast furnace slag, lime is added to remove it. So, then lime reacts with, or lime gets mixed up, not really, lime at the hot condition gets mixed up with the clay, that is silica, and these two together then form what is called slag. The slag will be floating over the molten iron, which can be drained from the bottom, and slag is taken away, floating slag is taken from the top. When you grind it, granulate it, this also contains both lime as well as silica. Therefore, this also can react under conducive condition. So, this also shows some similar property as this, but before that it can also show some sort of cementing property. So, these are the main pozzolanas. Besides that, silica fume is relatively recent addition to the classes of pozzolana. This comes from silicon and ferrosilicon industries, where quartz is heated up to high temperature as high as 1800 degree centigrade to obtain pure silica, and the the fume that comes out when it is condensed, what is produced is called microsilica, contains largely silicon dioxide alone. The other materials are very small and is extremely fine size. This material is very important because this is the one which has made it possible to generate, produce high strength concrete, very high strength concrete, or even high strength concrete, some of those high strength concrete itself. So, this is another one. Rice husk ash is another kind of pozzolana. Rice husk ash, if you process it up, finally it will be silica. So, if you process it up, you can get another pozzolanic material, because husk, when you burn it, rice husk, when you burn it, it will, carbonaceous material will burnt away, leaving the siliceous and aluminous, those materials, and they will form the pozzolana. So, one thing common in all this case, they are silica alumina material, largely silica in many cases. They are heated up and cooled very rapidly. Generally, they have amorphous structure. The reaction, that is pozzolanic reaction, is S stands for silica, CH is calcium hydroxide, and water produces CHS gel. Now, if you look at it, C3S and water was producing CHS gel, but it was producing CH as well. So, this CH, if I put some amount of this pozzolana in the cement, cement will react with water forming calcium hydroxide, and this calcium hydroxide can react with the silica in presence of water to form the CHS gel again. This is called pozzolanic reaction, and in blended cement this reaction is very much utilized. Typical, some of those pozzolana just I have listed down. For example, fly ash at type F, I will discuss type F later on, and type C is another kind of fly ash. You can see SiO2, silica fume SiO2 is more than 85% in fact, GGBFS SiO2 is of this order, and Al2O3 aluminum oxide. So, their oxides are same as cement. In ordinary Portland cement, this was around 64-65%, this is around 20%. If you recall, only thing is the oxide, same oxides are there, but the oxide composition, quantity of oxides have changed. Now, here CaO varies from 5 to 10% is type F fly ash, in type C it is 10 to 40%, silica fume less than 1%, slag it is 30 to 50%. As SiO2, you can see the silica in this is of this order, where this is very high. So, same oxide as the OPC cement, but the proportions are different. Largely the SiO2, which can react with wherever SiO2 is large, this shows extremely high pozzolanic reaction. So, these materials can be put into the cement and partially mixed up with the cement clinker to form what you call blended cements. So, pozzolanas are added, make composite cements adding maybe more than one or two of these ones. So, today there is all possibilities, you can add up cement, fly ash, slag all together and make cements, utilize the best property of all of them. So, blended cements are essentially cements where we add one of the pozzolanas together with cement, blend them together. Fly ash together with fly ash, when Portland pozzolana cement is produced, what is done is you actually take the Portland cement clinker, one of the popular routes, there are other routes also, Portland cement clinker, grind the fly ash together with the gypsum to get what is called Portland pozzolana cement. By proper grinding and adding additives, you can actually compensate for somewhat slow strength development in case of pozzolana. Pozzolana strength development is relatively slow for two reasons. One, the reaction itself is relatively slow. Second reason is that pozzolana depends upon reaction of the pozzolana depends upon the reaction of the pozzolana depends upon the reaction of the cement, because calcium hydroxide, when if it is produced, then only the pozzolana can be can react with the calcium hydroxide. So, this is we will discuss this sometime later on when we talk of mineral admixtures. Now, let us see the schematically where the oxide composition stands. For OPC, this is OPC, this is OPC. For OPC, this is OPC, this is OPC. Now, calcium hydroxide is around 60%, very small quantity of Al2 and relatively small quantity. So, calcium hydroxide 100% is here, 100% Al2O3 is here and 100% SiO2 is here. So, you can see that it has got high CaO, small quantity of SiO2 and small quantity of Al2O3. You come to pozzolana, it has got high SiO2, right, and small quantity of Al2O3, small quantity of Al2O3. Sorry, this will be this will have similar Al2O3, not this one. So, this will have parallel lines has to be drawn, right. This is the Al2O3 line maximum, CaO line will be like this, CaO line will be like this, and SiO2 line will be like this. So, SiO2 will increase in this direction, together. So, this one has got this much amount of calcium hydroxide, because calcium hydroxide 0 is this line, 0, 100 is here. Calcium hydroxide is small in pozzolana. Slag, it is somewhat higher calcium hydroxide, calcium oxide, but less than the OPC. You look for SiO2, SiO2 is 100% here, this has got maximum SiO2, slag still has got more SiO2 than OPC, OPC has got this much SiO2. Aluminum oxide 0 here, 100% here. So, all have got low Al2O3. So, you see that oxides are same, only proportions are differing, and this diagram also shows same thing. Now, let us see their hydration characteristics. If you see hydration product of Portland cement, this was my Portland cement, and recall these are inner product. H stands for hydration product, gel, inner product. This is inner product, this is the Portland cement, original grain boundary, and so is this is hydration product. This is my aggregate, and here I will have calcium hydroxide coming into picture. This place I will have calcium hydroxide C, which is non-sealing precipitate. So, here I will have calcium hydroxide, non-sealing precipitate of calcium hydroxide, right. So, this is what you will have, calcium non-sealing precipitate of calcium hydroxide you will have, and outer product, obviously the outer product will also be there. Now, if I look at, right, and this will fill in gradually as much as voids it can fill in, but if you look at reaction with slag, this is my Portland pozzolana and this is my slag. Now, slag, remember, has got calcium oxide also. So, it has got almost cement like composition, only thing is it has got less calcium hydroxide. So, it should react with water itself, but it does not, it reacts in presence of an activator. So, if you can activate the slag, slag will react. If you can activate the slag, slag will react. So, the activation of the slag is required, and cement, various materials in cement, when it reacts with water, for example, gypsum, alkalis, etc., can act as an activator. So, slag is an slag can also hydrate, and hydration product of slag is here, and because it has got excess silica, this can react with the calcium hydroxide that was there originally, and it can produce Z, which is pozzolanic material. We said that Z is nothing but for product of pozzolanic reaction. So, you will find that pozzolanic reaction product is here, and since it is more CHS gel and not calcium hydroxide, calcium hydroxide is actually a non-sealing precipitate, does not have bonding capacity, but CHS gel has. So, slag converts excess silica in slag, converts the calcium hydroxide into CHS, which is more of a bonding or sealing material. Thereby, it provides better microstructure in terms of cementing property, porosity, etc., becomes capillary porosity becomes lower. So is the case with fly ash. These are the aggregates, this is the aggregate, this is the pozzolana, but then this does not react on its own, this does not react on its own, right, and calcium hydroxide coming from here can produce pozzolanic material here and seal. So, calcium both these materials consumes calcium hydroxide and then seal does a non sealing precipitate is reduced out. So, blended cements are produced from this. One important issue is that such cements, when you produce by intergrinding gypsum, clinker and the pozzolana, their strength, initial strength is lower, but long term strength is better, particularly with fly ash. And so is the case with slag, but silica fume can show you high early strength as well. We will discuss this sometime later on. Composite cements, Portland pozzolana cement, Portland silica fume cement, Portland limestone cement. Now, this limestone is just a new you can add small amount of limestone. It is not purely inert material, so 15 to 17% limestone has been added to the cement system, and it has been observed that it can form compounds like calcium monocarbolaminate, which has got some sort of bonding properties. So, some amount of limestones are used, but otherwise limestones are used as a filler. Definitely, it definitely is a filler, increase the paste content or cohesiveness of the paste. So, this we will discuss sometime later on in the case of mineral admixtures. Portland cement with raw mill dust. So, raw mill dust, that is dust of clinker or dust of limestone, they can be added to fine lime, that can be added to the cement, and they seems to also improve properties. Some of them go into the blended cement as well. So, you can have multi component blended cement, for example, slag, fly ash, everything together. There is another cement with high belite, that is C2S, high C2S cement, that is something like modified cement. Strength development will be slower, and very high strength system like densified with small particles and macro defect free formulations we will discuss in the context of high they use silica fume, some use polyvinyl alcohol. We will discuss about this, and high alumina cement combination. We will discuss about this when we talk of high strength material. So, these are other such formulations, cementitious formulation. Well, benefits from the supplementary cementitious materials are, since they you reduce down the cement clinker, carbon dioxide emission is reduced. Fly ash being an environmentally hazardous material can be stored, can be used in cement, therefore, they can give you sustainability. In high volume fly ash concrete you use as much as 50% fly ash. We will discuss this sometime later on. In high performance concrete, silica fume is generally used, high strength concrete in fact, very high strength concrete MDF, DSP and RPC use silica fume, but it is costly, very costly in Indian scenario, 7 to 8 times that of cement. Potential of rice husk ash is, well, it is yet to be really verified and getting popular in this country. One more cement I will just before we stop is the high alumina cement. This was used very much earlier, generally produced from limestone or chalk and bauxite with small silica. So, this will have high quantity of calcium aluminate of kind Ca and C5A3, not C3A, but this is the product that is formed. The first product formed is calcium CaHT H10 after hydration, slightly different than what we used to get earlier, but this product is unstable and it gets converted into C3A H6 finally. Since this occupies more volume than this final product occupies less volume than the original material, thereby causes what is called extra porosity. It results in porosity in the structure, final hardened structure, because of this phenomena known as conversion. No rapid shedding, but early strength and rapid hardening, this has been observed. Absence of calcium hydroxide results in better sulphate resistance, but this cement, because of this conversion phenomena, is not really popular. It is a high alumina cements are good refractory material. Well, so therefore, today what we looked into is the cement types, lime, supplementary cementitious material. We will discuss about the supplementary cementitious material more in detail, because they not only you can produce them in with cement, you can use them in cement, but they can be sometime, I mean they can be added directly. Of course, sometime I said is correct, because you are adding one more ingredients into the system. So, they can be added directly to the cement concrete as an admixture. So, at that point of time, some of those issues related to pozzolana cement we will discuss, and we also talked about usage and advantages. The only cement out of all this is the high alumina cement, which is not being used much anymore because of this problem of conversion. Originally, it shows high, its original product formed has got high volume, final product occupies less volume, therefore, it results in some pore formation, and that is how it actually creates a porous structure, and it has not been found very suitable. That is how C3A cement its uses has been highly restricted.